So first of all, if my speech will start slurring and I start like talking rubbish, it's because of oxygen deprivation. So we all suffer of oxygen deprivation. So I will not take an offense if you just fall asleep. First of all, I would like to thank the organizers for inviting me to the House of Quants. I liked it a lot. And I would also like to thank my collaborators. So the work, most of the work on solving the parquet equations was done by two very successful PhD students. One of them will be looking for a postdoc. The other one already found a postdoc. So Mark Ritter is already the one that found one, and Stefan Roskap will probably be looking for one next year. And it was also in larger collaboration with Hiroshi Shineoka from Saitama University and Jan von Delft. Okay, and of course, Markus Wallerberger from the Wien. He also mentioned the parquet equations, and I'll try to continue a little bit more in detail on that. How do you solve self-consistent two-particle equations with quantics tensor trains? Okay, so this is like, in a nutshell, what I will be talking about. So I have very complicated multivariate functions called vertex functions that have some structures, but they really take a lot of memory. I would like to, okay, great. That's not what I want. I would like to do calculations with them, which is hard. So I compress them using quantics tensor trains, and then I do operations on the trains that correspond to the equations, the hardest of them being the Bethe-Salpeter equation. And let me first start with some physical motivation. What are those functions that I would like to calculate? So if I want to get spectra, I need one particle Green's function. So this is something that is measured almost directly. And in all what I will be showing, this is just a single line. The single line is given by, it's the Green's function of the system. It can be exactly calculated if I have the full, all the eigenvalues of the Hamiltonian. But that's not what I want to do. I don't want to calculate it directly. I want to solve self-consistent equations in order to get it. One of them we saw on Max talk is the Dyson equation, when I can also do that in a self-consistent manner with some approximation how the sigma is depending on the G. And I can also do something for the two-particle objects that are measurable. So for example, I can also measure magnetic susceptibility. But this is a so-called two-particle quantity. It means that if I want to build diagrams for that, I need to take into account moving of two particles in my system. So I also have all kinds of correlations between the two moving particles in the system, which means I have also something which we call two-particle scattering vertex. And this vertex, like if I take it similarly to the Dyson equation, has a corresponding equation which is called the Bethe-Salpeter equation. And it means that I can generate more diagrams that are in this vertex by taking a smaller part of diagrams and connecting it with a full vertex, very similarly to how it looks like in the Dyson equation. Now, what do I take for this irreducible part? For self-energy, I don't know, I can have some Hartree approximations. Here I also can do that. I can take just the interaction as this two-particle vertex, just the two-particle Coulomb interaction. And there are many other approximations. What I will do today is to take one of the most complicated approximations for that vertex, actually to get it from the parquet equation. Why is it complicated? Because that irreducible vertex is given by equations which involve also the full vertex and another irreducible vertex and another irreducible vertex. So it's just a lot of work. And finally, I can also have a relation between the two-particle vertex and my original Green's function line. And all of that actually is a way of self-consistently obtaining all of the quantities here. Okay, and then I can, of course, calculate the observables. So I can calculate magnetic susceptibility. I can also analyze it. What are the important contributions from which parts of these vertex equations they come, and also do such analysis, for example, for the Green's function. It gives, apart from the observables themselves, a little bit of more information about the system and actually helps sometimes to construct approximations. But, so let me be formal. Formally, this two-particle vertex is the connected part of the two-particle Green's function. So I subtract parts that are just products of one particle Green's function, and then have the connected part, and I also have to divide by the 4 legs. What does it mean? It means that it depends on all kinds of quantum numbers that are connected with the incoming and outgoing line, momenta, possibly orbitals, spin indices, and of course, I work with frequencies, but I could also do it in time. But it would be also depend on 3 frequencies. So I have already here momentum and energy conservation, but I like to show it that the sizes of these vertices easily get extremely large. So this is a predicted size. I've never constructed anything that would be that large, of course. So what is in that vertex contained? So if I just take diagrammatic expansion, I like Feynman diagrams. So the dot is the U and the lines are Green's function, but here are only these 4 outer lines are only to fix the numbers of the outer legs. So it's just, it starts with the interaction, and then I have diagrams on diagrams on diagrams. Each diagram is a nested integral, and you can also calculate them directly as sum of you do, or we heard today in the earlier talk on weak coupling TCI. So in principle, one can just directly sum the diagrams. For evidence, maybe a little bit more hard, but for the Green's function, you can do it, for the two-particle Green's function even. But that's not what I want to do. Instead, I want to do a diagrammatic classification. I want to classify these diagrams into classes because I want to do resummation because I know perturbative expansions sometimes don't capture some of the physics. And how about doing some full resummation? So I categorize these diagrams into classes of reducibility. I would have diagrams that I can cut into by a cut in the particle whole lines. So it's about separating the outer points of the vertex. So it's not that complicated, but it might look complicated like that. What is the difference between the channels? So this would be separating them in the particle hole channel. This would be particle hole transversal because this is like particle hole lines. And these two are separated from these two. And these diagrams would have like a particle-particle separation when I separate these two from these two. So a bit more complicated. And order by order, the diagrams get more complicated, but they always belong to these 4 classes. So particle hole reducible, particle hole transversal reducible, and particle-particle reducible. And I also have a class of diagrams which is called fully two-particle irreducible. They do not fall into parts. And I have this box for each of these classes. In particular, that is a box that I take as an approximation. I have to approximate that one because for the other boxes, I can actually formulate Bethe-Salpeter equations because like these particle hole reducible. So I can say I generate all diagrams if I connect irreducible diagram to the full vertex, right? So irreducible diagrams times all diagrams will generate me everything. So reducible, and then I have everything. So my full vertex is composed of these 4 classes of diagrams. And if I can calculate all 3 of them and have an approximation for this one, I have the full vertex. To that, as I already was explaining, we also have a connection between the Green's function and the full vertex, and of course the Dyson equation. Now, this is an old method. It has been proposed already in the 60s, and it came back in 90s because of some works of Pickers who made it work for some cases, make significant simplifications that go under the name of flex. And but the full solution stays difficult because, of course, let's come back to that. These vertices are just very, very large. But they are also very structured. There are prominent structures on diagonals and sometimes shifted. So these vertices are actually quite old. They come from a momentum and frequency representation on equidistant grids that was quite old already in 2019. But the momentum grid was like 6 by 6. So here is the frequency dependence of the vertices for different momentum points. And this is the dependence only on 2 of the frequencies. These are discrete Matsubara frequencies. And you can see that this is so these vertices are not that big because of the small resolution. But by no means there's that much information in those vertices. However, if you try to just directly approximate it by taking only this cross or only this diagonal, it basically boils down to some perturbative expansion. So I never know how large are these lines that are going to be here, in what way they are, how large is the inner part, how important it is for the physical quantities. That's why I would like to have an agnostic approach, and here the QTTs come in. So maybe I don't have to explain, so that would be just the representation for a one-dimensional function for momentum. I just discretized momentum. And what I do if my function, my discretized function is then mapped on a matrix product state or tensor train and approximated with a finite bond dimension, right? So if my vertices are compressible, I will expect that the bond dimension or rank will be low. So let's try. First of all, we have a different notation in some of our papers because of the fact that we also calculate susceptibilities or show susceptibilities, which are chi. That's why it's sometimes safer to use D for the bond dimension and not chi for the rank, but it's the same. So now we have, let's say we focus for first on frequency dependence, not on momentum dependence. Why? Because we have good benchmarks for that, and it's good to start with something that we know what the exact solution is. So the frequency dependent of a vertex is represented by a QTT with interleaved representation, where we group the same scale together. It's not the only way. It turned out that for the bond dimension, for the particular problems that we looked at, that's the lowest bond dimension. But it doesn't have to be. And I have some, as I said, I have some exact benchmark. There's a model that is just a single atom, well, not atom, single site. If I speak to chemistry audience, they always laugh at me if I say Hubbard atom. What atom? What atom? It's not an atom. It's just a single site on which I can have from 0 to 2 electrons, and if there are 2, then they pay a price of the Coulomb interaction of the Hubbard U, and there's some chemical potential to it. And it turns out that for this Hubbard atom, you can solve this problem exactly on paper. But in order to calculate the 2-particle vertex of that atom, it's quite a bit of work. But you can still do it analytically, and you can get the exact vertex F and all the other vertices that I was showing as boxes before. So it's an excellent benchmark for our compression methods. So first of all, if these vertices are compressible, well, it turns out actually yes. So for a given tolerance in TCI, we can compress them with relatively low bond dimension. It does not depend on R much, R being the length of the train, so how many Matsubara frequencies I take. So these are discrete frequencies, so R is just representing the range of frequencies, not the resolution, but the range. And if I now push the tolerance, you can hardly see that there's a difference, right? So the bond dimension does grow, but not that largely. It is probably partially because these vertices are only for an atom, so they have very sharp structures that are very localized. Again? Temperature. Yes. So in the Hubbard atom, there's only one parameter that is combined U times beta. And for this particular calculation, it was here, I think 50. So, but let's see. I have some temperature dependence later. Good question. Forgot to put it on there. Okay, so let me now get to the equations themselves. So I have compressible vertices. I have a QTT that represents a vertex. Now, in order to solve my parquet equations, I have to map the equations on operations in the QTTs. So on finite grids, there's a lot of work done on parquet equations. I would particularly like to indicate the newest work that is very promising. I think combined with QTTs that could bring quite a lot, done by Fabian Kugler and collaborators. And now in QTTs. So what do we have to do? So first of all, the parquet equation, when I add these reducible vertices, for reasons that I have these Bethe-Salpeter equations in different channels, I end up with variables that I need to shift. Well, this shift of variables in an equation is very mean. So if you have a distributed memory vertex in which different parts of that vertex are spread all over your computational cluster, then basically all your time of your computation is spent on memory access and exchange and everything. So with InfiniBand, it's already fine, but in older times, it was a bottleneck. Now, the next one is the Bethe-Salpeter equation, which is more like matrix multiplication. It is done on finite grids with matrix multiplication just, and the Schwinger-Dyson equation is more of the same. And then you also have this fact that you need to solve everything self-consistently. So in QTTs, this variable shift can be actually represented as a relatively nice MPO with low bond dimensions. So this goes under the name of affine transformation, and the bond dimension is, for this particular transformation, I think it's 11, so nice. And then the Bethe-Salpeter equation can be decomposed into MPO contractions in a slightly more complicated way. It's just because we have the chi0 that is a diagonal one, and we have to add some indices in order to make it work. But this is rather straightforward, so we can look at performance. Okay, so the bottleneck is the Bethe-Salpeter equation. So the performance of the Bethe-Salpeter equation, it decides about the performance of the entire scheme. So this scaling is important. So the predicted scaling of runtime is dimension is the bond so maximum bond dimension or rank to the fourth times r, and it actually figures. So we have such scalings. And what is important, it doesn't quite depend on R very strongly, so on the length of the train a little bit, but here it's the prefactor is not so large. And for different bond dimensions, we have linear scaling in the length of the train instead of having exponential scaling in R. Exponential to the power of 4, actually. Because that's how the frequencies scale. And the error depends on the bond dimension that I used, and it is put against the exact value. So the error is just the difference between the exact value and I think normalized difference between the exact value and the value that was calculated through the BSE. And the dashed lines are the traditional grid calculations, which we could do on the single node of a cluster up to r equal to 9, I think. Then it wouldn't fit to the memory anymore. So scaling with the bond dimension is very nice because the error goes exponentially down. Okay, very, very nice. So let's look if we can do actually a self-consistent calculation. So we could have error accumulation, all kinds of stuff, but we don't observe it. So for relatively mild parameters, it goes smoothly with relatively low bond dimension. So even if you have a maximum bond dimension of 100, the error is around 10 to the minus 3. And with higher bond dimensions, I can push the error quite a bit down to 10 to the minus 4. And there is this atom, although it's extremely simple, has difficult points where this fully irreducible where this irreducible vertex gamma actually diverges. And very close to these parameters is such point. So we expected that if we just don't push the bond dimension high, we will not be able to converge it. But actually, it did converge. However, the time, the number of iterations was actually quite large. But we didn't do any acceleration of the iterative schemes, so we were just happy that it eventually converged. Okay, but now, how does it scale with temperature? So with temperature, as we go from beta 1 to beta 50, at u equal to 1, these vertices, they grow a little bit, but they can still be quite nicely fitted with low error. However, the bond dimension does grow with temperature. If you look at this plot, it shows the maximum bond dimension versus 1 over temperature times u at u equal to 1. And then at 2 different tolerances. So we have it at the lower tolerance and the higher tolerance. The higher tolerance is 10 to the minus 6. I think it's too small for you to see, but it's 10 to the minus 6. So if we take the bond dimension here, it is already over 200. So if you have like 4th power scaling and it's only frequencies, no momentum, it's already quite bad, but it does seem to saturate and even go down for this particular model. So why does it happen? So we don't have that much proof, but at this particular point, what happens with the model is that there's a divergence of the irreducible vertex gamma, but not of the F. The F, if you look at beta 5, that's somewhere here, it doesn't look really diverging. The maximum value is around 1, right? And even if you go lower in temperature, it's like 5. But that vertex gamma actually has points where it diverges, and this is one of the more important points with some global divergence that doesn't depend on frequency. And in that point, it seems that it's something happens in the model, and then the scaling with temperature is different. The question, what happens in the model, is a subject of study in Vienna by Alessandro Toschi and all collaborators for many years now, both in the atom and also in the Anderson impurity model. So in order to understand a little bit what important can be happening there, let's go to the single impurity Anderson model. So first, we did calculations at weak coupling. It's also in that paper. So small values of the interaction for this Anderson impurity bond. It's more complicated than the atom because we have the atom that is coupled actually to the bath of electrons. The electrons in the bath are not interacting, but they hybridized with that atom. They can hop there and back, and because of that, you actually have quite a correlated system. We did the calculations for the flat band density of states, so the non-interacting electrons are in a flat band at half filling and in parquet approximation. That means that I only take the one diagram of the fully reducible vertex. So it's called weak coupling, but it means I miss some of the diagrams that are 4th order or higher. And the reference data are from state-of-the-art parquet approximation implementation on equidistance grid. Okay, and then the exponential scaling when the bond dimension is retained also in this Anderson impurity model, and we also have convergence as we do iterations actually quite quick. The problem is that in the parquet approximation we don't really have Kondo physics. The interesting physics that is connected with the vertex divergence that was on the other slide is actually not present in that particular approximation. It's too approximated. So in order to look at it more carefully and what happens with the bond dimension, actually Hirona Ishida, who is here maybe, who was here, did some calculations with exact diagonalization, and then we analyzed the bond dimension as a function of the parameters of the model with a particular focus on the regime when the Kondo physics takes place. Now, in order to get a little bit of a physics picture, let me show you the magnetic susceptibility first. This is magnetic susceptibility or spin susceptibility. Okay, this axis is the same as here. So this is as a function of the strength of the coupling to the bath. And here we have the interaction, the local interaction on the side. And then we have a regime where the susceptibility is very large. This is the local moment regime. We have a response because we have a local moment, and a regime where the susceptibility is basically very, very small, almost zero, where the local moment is completely screened by the electrons in the bath. And this is connected with the Kondo effect. So the Kondo effects happened here, and the local moment regime happens here. And now in the bond dimension, what we see is that the bond dimension not really grows with temperature, but it grows if we are getting near the boundary between the Kondo screening and the local moment regime. And this red dot curve is actually an analytic prediction for where this regime actually happens. It is based on some Pullman scaling ansatz done before, and it actually fits very well to the maximum of the bond dimension, not perfectly, but quite nicely. So the maximum rank is where interesting physics happens, right? So there is no free lunch on one hand. On the other hand, it happens only when we are in this Kondo regime. So not at low temperature, but around this Kondo regime. So, and it's still like manageable. For the record, so this particular solution is not approximate, but it is for a bath that was fitted with only modeled by the 3 sides. So of course there will be some artifacts of that calculation, and one would have to check if the scaling with temperature is not worse if we look at other representations of the bath. So that's probably a little bit different. However, the maximum of the bond dimension being here can be somehow understood. So we make the train in such a way that we separate the scales, and each scale is represented by a qubit, right? So it's like spin, and then the qubits have these correlations between each other. And as we get into interesting regimes, this correlations of qubits, so the entanglement of these auxiliary qubits becomes larger, and one can translate it into entanglement of time scales. And this was actually the topic of the talk of Markus Wallenberger on Monday. So I will not talk about it more, but let me move on to what we would like to do from the parquet with the parquet equations. So the most interesting is actually what happens in all these scattering channels in a full momentum-dependent system, because there we can, for example, in the Hubbard model, we can look at spin fluctuations, we can look how these spin fluctuations influence, I don't know, for example, pairing or some charge fluctuations. It becomes interesting there. But for that, we necessarily need momentum dependence. However, when we look at the momentum dependence of just the Green's function, and for some value of the omega plus u that is not 0, and some small broadening, as a function of this broadening, so this delta here is 10 to the minus 1, 10 to the minus 2, 10 to the minus 3, and the bond dimension here is capped by these values. Okay, maybe I have to, this is a patch bond dimension. Maybe let's just first look here. So that would be the bond dimension as it is, but by accuracy that maybe Gianluca can tell me. What was the accuracy for the bond dimension? Do you know still? The tolerance, yes. 10 to the minus 7 or something. So quite large tolerance. So quite small tolerance. And then for this particularly thin delta, if you just compress this Green's function together, so the momentum dependence of this Green's function, you get a very high bond dimension. It's like 2000, maybe. This is a logarithmic scale. No, this is a linear scale. So it's like 2000. So it's really large. So for broader deltas, but even if you have like 0.1, it's already 200. So the way out of it is actually to distribute the tensor into patches. And this patching actually allows us to cap this bond dimension. So we could just make a cap on the bond dimension and see that we then adaptively get more and more patches for this cap bond dimension. And then for this particular case, we see that the bond dimension of the patches is significantly lower. And one would think, okay, it's useful because if I have like the tensor trains patched, so I cut them out and divided them in many tensors, so I can distribute them, I can use it for parallelization, or I can, I don't know. It might be useful because the other tensors then have lower bond dimension. Then what one would not expect that one wins something. However, one wins because in this way, we also take advantage of sparsity. So this Green's function, this is a real part of the Green's function, has only some important behavior in selected regions of the Brillouin zone. The rest is basically smooth, trivial, so it doesn't really need those large bond dimension, right? The lower red curves are for the patches that are actually, yeah, practically boring, and the upper red curves are for the more interesting patches. So as we will show in a forthcoming paper by Gianluca and others, then that it will actually, it brings advantage, not only because it can be parallelized, or not only because then we don't have to cope with large bond dimensions, but it actually also takes advantage of sparsity. So we focus on structures that are there, more like adaptive integration, right? So it's not a different concept. Okay. So I don't know how much time do you still have? 3? I don't know. Much more. Okay, I was. Include questions. Okay, so 5. Okay. Okay, so if I have time, then let me show you something more. So, okay, but what about the momentum dependence of vertices? So momentum dependent on vertices, if you look like at 16 by 16 calculations, it's like sweater patterns, right? It's relatively low interaction. It's also, this is a Hubbard model now. Sorry for not having the Hamiltonian. But the Hubbard model is more like this Anderson impurity model, but you don't have the bath, but each side has the interaction, and between each sides you can have hopping. And this model is relatively hard to tackle with these parquet equations. It's hard to tackle in general, but maybe parquet equation is not the best way to solve it. However, it can bring us maybe some additional information that we don't have in other methods. Now, this is weak coupling, relatively high temperature for this particular model. At fixed frequencies, the bosonic frequency is fixed to 0, and the fermionic frequencies are like fixed to the first Matsubara frequency, positive, negative. And then we fixed also the bosonic momentum, say at pi, and or 0. Now, here is a different bosonic momentum, not so symmetric. And then we look at different vertices. So this is the reducible vertex in one of the spin channels. So these vertices always occur apart from the orbital indices and momentum indices and frequency dependence. They also have spins, and it's usually enough to take some of the spin combinations into account. One of them being sum of different spin combinations, which corresponds to the density or charge channel. So that would be the reducible vertex in the charge channel along a path where the momenta in fermionic momenta. So remember, each vertex is dependent on 3 momenta. 2 of them are fermionic, 1 is bosonic. And then it's along a path on the Fermi surface. So it's half filling, so Fermi surface is a square, and we go along the path for both of the fermionic momenta. Now, this is some decomposition of that full reducible vertex into some part which is called single boson exchange and the part which is called multi-boson exchange that helps to solve such large system. Well, large for me. Now, this pattern, it's not particularly sharp. It doesn't tell us much, right? So the purpose would be to look how does this momentum dependence actually look if we can look with infinite resolution? Do we get structures that in any way resemble the sharp structure that we get if we look only at the Green's function? Or I don't know. So yeah, so that's that's somehow the purpose of further calculations, because basically more than the 16 by 16 at this temperature basically does not go, right? So 100,000 core hours to just get just such few pictures for one particular parameter set, it's not very good, especially that it's only 8 Matsubara frequencies for the core vertex, which means that the times are really, so it's not really enough to go to lower temperatures to study superconductivity and so on. Okay, so yeah, we're stuck with compression. Maybe I would like to, so the patching paper with Hiroshi as well will come at some point, and with Jan van Delft and Mark and Stefan and so on. This, please await it with impatience. And I also would like to advertise the bond length, the bond dimension, and as a measure of length scale entanglement of another paper. And the take-home message is the QTTs seem to be a good compression tool for two-particle vertices, and let's see. Okay, thank you.
Okay, questions?
Coming back to your interpretation that, when you go to the Fermi liquid regime, it's simpler than at the temperature between the transitions. The thing I don't really understand is that what you're compressing here is a function of frequencies, right? Two frequencies.
Well, here actually, this is a two-particle, I didn't say what it is. This is a two-particle Green's function compressed in
It's
times.
a function of two frequencies.
Yeah, it's impurity model of three frequencies.
But as a function of frequencies, I will have frequencies at very low frequency, which will be, low energy.
Yes.
But I will have intermediate frequencies as well that go very far. So I will not have just a Fermi liquid aspect into it, right? I will have all sorts of crossovers. So it's
sure. So it's not for the Hubbard model. It's a simple impurity with flat bands, but the density of states, it's not much happening more there. So it's, of course, yes. So it's just okay. So you want to say that I also can get deep in the Fermi liquid large bond dimensions. I can, but I don't think without DMFT. I think in DMFT, yes, but because then I don't have a flat band density of states, but then I have, sure. This is just, so, I mean, bond dimension of 200 is not that small. So this is even higher here, 250 probably. So, yeah.
Okay, but then there is.
So on the first slide, one of the gamma, as I understood, is an approximation.
On which slide?
This one.
This one.
The red one is an approximation,
yes.
Right? And how can we evaluate the quality of this approximation here?
Good question. Yes. So perturbatively, so it's already hard to include that diagram and doesn't help much. So we can do parquet approximation when this is U. If we do the parquet equations for the Hubbard model, we can take this fully irreducible vertex for exact solution of a effective impurity problem, which means from DMFT.
Okay.
And then this vertex is actually quite large. It's by no means perturbative. If you go beyond U equal to 2, it becomes larger and larger. And for U equal to 4, it's actually very large. And it is local from the DMFT, right? And it also is built only from local diagrams. And this is actually quite a strong approximation that is claimed to be insufficient to describe some of the physics. It is open how much momentum dependence you need to include. There are some studies if you include some momentum dependence, but in this diagram and in parts of this diagram at the same time in the framework, which is called cluster single boson exchange approximation, then you capture a little bit more of the nearest neighbor physics by taking this diagrams that are here at a non-local level. But on the other hand, because it's so difficult to calculate it, you cannot treat the multi-boson parts of these diagrams fully. So this is also an approximation that needs to be evaluated. Yes.
Thank you.
Just to follow the question.
Yeah.
Can we benchmark that on the regime where we have the density solutions?
They can't. They refuse to calculate it.
We can
And so,
calculate.
yeah, we can. I asked them, why don't you calculate the fully reducible vertex?
Oh, okay. No, that was the final solution. It's not easy to compute lambda.
Yes. So sigma, if you compare the self-energy, actually, even with the local vertex, it comes out quite nicely.
So Matthew was asking about comparing the solution of the wedge.
Yes, the final solution. The problem is that you cannot disentangle it from discretization errors in the momentum grid at the moment.
Any more questions?
At the end, you were showing this momentum dependence of the vertices, right?
Yes.
So you wanna compress also this?
Yes.
Sort of
No,
matrix?
well, this I don't want to compress. It's 16, so it's R equal to 4. We
Yeah,
already
but it's larger, right?
checked. You cannot compress something that is so.
But my point is that like this lattice of circles will have a huge one dimension in my experience, right? Like the same way as a Fermi surface that is a circle.
I expect so.
Yeah. So I mean, what would you do in order to like compress this?
Patching,
Well, then
smart
it's like
ideas.
A lot of patches, like everywhere.
Think about it. Think. Yeah. You have your GW 32 by 32 is still not perfect, right? Think about it.
Yeah, because what happens if you do like a DC field in non-equilibrium Green's functions? This is what the pattern that you get. That's how the Green's function looks.
Oh, really?
Because you have Bloch oscillations, and
Yes, okay.
and you don't. I don't know how would I approach this if I wanted to do such calculations. So that's just...
The bottom line is I don't know. So for the BSc, some preliminary results with momentum dependence Samuel had on the poster, but it was the momentum dependence was in one dimension, right? The momentum dependence was only in one dimension, right? For your BSc. Okay. We'll see.
Any
So-
more questions? Well, if not, let's thank the speaker. We had